Hello. Basically, over the course of the first couple weeks of BC, there's been a particular problem that's popped up a couple times, and not a lot, but it's popped up a couple times, and it's something that we normally taught at the end of Calculus AB, and in fact it was planned for. There's even a nice rich problem set for you to work with video solutions, but unfortunately stuff happened in March, and we never got to get to either of those last two lessons. Some of those were taught in Calc Prep, like the second fundamental theorem and optimization. One of them was not. This really short lesson about taking the derivative of an inverse. Not an inverse trig function per se, although this would theoretically work with some of that, but with inverse functions, like a function's inverse. So since so many people have asked about it, I wanted to just briefly go through that information and post this video in case you wanted to actually catch up on that information. It's a small topic, but at the same time it's kind of an interesting one, and it uses the definition of inverse in a really neat way. And it's honestly a topic that I don't mind talking about, so I'll run through it here just to kind of give you an idea of how to approach this. So first of all, on this page, like, it introduces things like a normal lesson would. On the left, though, I've sort of added a quick little piece of information to throw out there. Oftentimes people get the idea of inverses and reverses sort of confused. The inverse is a particular function or a particular relation that is related to another relation. It's not the best explanation in the world. I'm failing this right now, but that's what I get for trying to make it at 9:30 p.m. So in any event, what you can see here are the two different pathways that you could take. And you'll notice the answers at the end of each pathway are very similar. There's just one small difference. To talk about an inverse, the inverse is the relation that switches the inputs and outputs. And the best way to describe that would be this. If you have something such as f of a equal to b, then what f inverse does is it says f inverse of b is equal to a. So it literally switches the inputs and outputs. Now if we want to find that inverse relation, the way we've always done that is we take our original and we switch x and y. So instead of y equals the cube root of x plus 2 plus 1, we get x equals the cube root of y plus 2 plus 1. And then to find the inverse itself, we solve for y. That's a little different than the process that we use, say, when we're finding the volume of a solid of revolution and we revolve about a vertical axis of revolution, where we just literally solve for the other variable. It's the same relation, but it's not, because x and y are in different places. This one has the exact same it's the exact same shape as the original. This one is a reflection across the line y equals x. Now we're not going to talk too much about that geometric interpretation, although there's some rich information there if you want to investigate it. Instead, we want to focus on using the definition of inverse, as well as some intuition based on linear functions, to develop this sort of simple relationship for how to determine the derivative on an inverse without knowing the actual function. So that's going to be our goal here. So to kick things off, I mentioned the fact that I really wanted to think about the really clean and simple examples to kind of build some intuition about what's going to happen here. We're going to do that by investigating the inverse of a linear function, simply because those are really easy to work with. And as it says, or in our little brain tree up here, I want to point out that the thing that we always kind of stick in our minds about inverses is that they switch x and y. That's that whole reversing the input and output thing I mentioned on the previous page. That tends to be the number one thing that we associate with inverses. I mean, yeah, there's also this whole thing about reflection across y equals x, but for the moment, that's not going to be our focus. I'm going to try to simplify this just so that I've got this video to post for everyone. So what would we do in this case if we want to find this function's inverse so that we can maybe talk about its derivative? It's going to be the plan here. Well, we'd first write our function, f of x equals 5x plus 2, as y equals 5x plus 2, because that would then allow us to switch x and y. From there, we could do some algebra. We could subtract 2 from both sides. And we could divide both sides by 5. And when we do, we get this new relation, which I'm going to rewrite as 1/5 x minus 2/5. And this is what we would call f inverse of x. It's the relation or function. I mean, I think it's supposed to be actually, this one will for sure be a function, obviously, but depends. Basically, this is the relation that takes the outputs of the original line and spits out the original inputs. So let's test that out for a second just to confirm that this did actually work the way I've described it. So let's pick a number. Let's say that we want to compute f of 1. So obviously if we plug in 1, we get 5 plus 2 is 7. So that means the point 1 comma 7 is on the original function f of x. The question is then, what happens if we plug in the output into the inverse? Well, in this case, we'd have 1/5 times 7 minus 2/5. That's going to be 7 over 5 minus 2 over 5, which is equal to 5 over 5, which is equal to 1. So that means on the inverse, we have the point 7 comma 1, which is the literal flip of that original point. So there's this nice connection. Now, having done this quick little investigation, we haven't necessarily talked at all about slope, even though our title of the lesson is about the derivatives of inverses. So it's worth making one observation before we go forward. So basically a question that we could ask ourselves pretty easily, since we can see that both of these are lines, would be to compare the slope of the original function to the slope of its inverse, and to just see if there's any sort of relationship there that might be interesting. So in looking here, our original relation was 5x plus 2. That means its slope was 5. Our inverse, though, was the equation 1/5 x minus 2/5, which means the slope of the inverse was 1/5. So what this suggests is that there's some sort of reciprocal relationship here. Granted, it could theoretically just be a coincidence because the sample size of n equals 1 does nothing for us. It's definitely not mathematically rigorous, but it's pointing us in a really good direction. Since the line has the same slope everywhere, it's nice to be able to see that there is a reciprocal relationship. Not a negative reciprocal relationship, just a reciprocal relationship to kind of dig into. So now, how can we formalize this? How can we get anywhere and make sure that this is true rather than just kind of make it up as we go? And the answer is to go back to the definition of inverse. So here is a partial part of the definition of inverse. Let me adjust it a little bit here. Obviously, people aren't necessarily a big fan of the ify, or if and only if, but basically this is only true. F and g are inverses if and only if f of g of x equals x, and g of f of x is equal to x. I usually skip that step because in the work we're going to do, we're not going to use the second version here, but just keep in mind that that's the full complete definition. What this means is basically if you compose f of g or g of f, meaning that you plug one function into its inverse, you will actually spit out the original input. And this is kind of a cool thing. So just to kind of illustrate the thought process behind this, because this will kind of help us organize our work moving forward, basically I would say this. If f of a is equal to b, and I want to make sure I state this just correctly, then according to the definition of inverse, g of b should be equal to a. Right? Because that's just saying that we switch the x and y. We switch the inputs and outputs when we use the inverse. From here, a similar piece that's kind of interesting to see, though, would be this. If you evaluate f of g of b, that's the same thing as evaluating f of a, which is, of course, equal to b. And likewise, I mean, look at that. That's literally what we said here. F of g of x is equal to x. We started with f of g of b, and it inverses itself out, the original input. Likewise, we could go in the opposite direction. Again, not going to be as necessary for us here. But if we do g of f of a, that's going to be g of b. And we said at the very beginning that g of b is equal to a. So this is this kind of neat thing that we're seeing here that's really helpful to kind of get into your head. It's that if f and g are inverses, they undo each other. Just like other inverse operations do, like f and g undo one another. They just kind of unravel whatever's on the outside, and we're left with our original input. So keep that in mind. In particular, the structural idea, we're going to take advantage of it as we go and investigate the slope part and try to confirm whether or not that linear implication we saw about the reciprocal slopes actually does hold. So that's where we're going. The point, so reiterating the same point, this isn't necessarily worth its own time, but it says the point a comma b on f of x and the point b comma a on f inverse actually are describing the exact same point. All that's happening is they're being reflected across a particular line. So just as kind of a quick little geometric argument to kind of help sell you on this idea, of course it wouldn't cooperate. It's only 9:45 as I'm doing this. Couldn't give me a little bit of a help here. So basically imagine for a second that we've got some sort of function that looks like that maybe. And this is, let's call this f of x. So in here, according to what we know about inverses, or what we've mentioned in the past about inverses, the inverse function should be reflected across that line, y equals x. So basically we should see a shape that looks like that. So it's a perfect reflection across this line, y equals x. Most importantly, though, and what's being said on this page in particular, is sort of the graphical version of what we talked about f and a equaling b, or f of a equaling b. Basically, if we have a point a comma b on the original function, then the point b comma a is going to lie on our inverse. And the idea is these points are literally the same. One's just reflected. And of course, once again, now we're asking graphically, what is it that happens to the slope when you reflect that point? And the answer is that it does become reciprocal, like you do basically flip the slope. But we haven't proven that just yet, so let's do that. So here's our actual proof of how this works, or why this works. And we're going to use that same sort of setup that we did before. Let f inverse equal g, just because that way we don't have to worry about writing things like f inverse prime of x. Like that just looks, I think that's the formal notation. That's bad. We don't want to do that. So let's call f inverse g of x and let y equal f of x. In particular, though, I want to go a little bit further. So I want to basically establish some things here before we jump in and actually look at this. First, we're going to assume, and this is actually a proof. This is a pretty good proof, but I think it's a good one. Let's assume that f of a is equal to b, and let's also assume that f prime of a is equal to some slope m. Because our goal here, well, we'll see this in just a second. So from this information, what we have is we can guarantee that since g is f's inverse, that g of b is equal to a. The question that we want to answer is what is the slope at that corresponding point? And as I mentioned earlier, it's going to be 1 over m. It's going to be the reciprocal, but let's just hold off for the moment. Let's treat this as kind of our open question and see where it goes. So how are we going to prove these things? Like, what are we going to attack? Well, it comes down to starting things off the same way we did earlier. Let's use the definition of inverse. So if f and g are inverses, that implies that f of g of x is going to be equal to x. So simple starting point. What I'm going to do now is I'm going to differentiate that relationship with respect to x. And I'm a huge fan of this move. For whatever reason, this is one of those things that just kind of really impresses me. Took me a while to get comfortable with it. So we're going to differentiate with respect to x on both sides. So on the right, yeah, that's just equal to 1. Is what it is. That's a linear function. On the left side, though, we have the chain rule. That's going to be f prime of g of x times the derivative of the inside, which is g prime of x. And now as you can see right up here, we're trying to find some information about g prime of b. So I'm going to try to isolate the g prime of x. So what that means is I'm going to divide both sides by f prime of g of x. So I'm just kind of dividing by the remnants. It's whatever's left on there. Boom. So where does that leave us? Well, it now gives us as our relationship here that g prime of x is equal to 1 over f prime of g of x. So cool, I mean great, I guess that sort of helped. But remember, it says right up here that what we were trying to evaluate was g prime of b. So let's evaluate this entire expression at x equals b. In fact, it's the entire equation. We'll do the same thing on both sides. So that means that we're going to be evaluating g prime of b. Well, looking over at our right side, that's going to be 1 over f prime of g of b. That, according to what we said earlier, due to the properties of inverse, g of b is equal to a. So this is 1 over f prime of a. And then taking one more shot here, it says f prime of a is m. We just decide to call it that. That means that the slope at that corresponding point is 1 over m. So what we've just shown is that if all the rest of that is true, the slope at the corresponding point is the reciprocal of the slope at the original point. So pretty interesting thing here to pull out. I think typically this is expressed in this way. It basically says something along these lines. But really, this is the sort of relationship that we want. If you know the information about the original point and its slope there, you can just flip the slope at the corresponding point. As long as everything lines up nicely, everything's taken care of. And in fact, we're going to exploit this relationship in the work that we do with inverses when trying to compute their derivatives. So here is sort of the general summary, just to kind of like wrap it up one more time. So this is the organization that I use, sort of the structure. So basically, I list out the information I have, including the inverse implication. So the idea is if G equals F inverse, then F of A equaling B means G of B equals A, because we switch X and Y. And then from there, if F prime of A is equal to M, G prime of B, the slope at the corresponding point, is 1 over M. It's the reciprocal, not the negative reciprocal, just the reciprocal. So there's going to be the path that we follow. So let's look at a problem here and just kind of try it out. I'll do a pretty simple one, then I'll do a slightly harder one, and then I'll just kind of let this go. I think a 20-minute lesson is more than enough for something I'm just kind of throwing together at the last second. So our example says, it is known that f of 5 is equal to 6 and f prime of 5 is equal to 37. So in a sense, what they're giving us right now is just sort of an inventory of information about this function f. So I'm going to go ahead and record it, in fact. It says f of 5 equals 6, and it says f prime of 5 is equal to 37. So we'll start there. Next, the problem tells us that g of x is equal to the inverse of f of x. Well, that's actually a huge piece of information, because it means that g will switch the inputs and outputs of f. That means that we know g of 6 is equal to 5. And what we've just done is we've now sort of tethered 2 points together. 5, 6 on the original function, and 6, 5 on the inverse function. Finally, they want us to find g prime of 6. And you'll notice that that's a really fortuitous thing that they want us to do, because g prime of 6 is the slope at the corresponding point to the original point that we had a bunch of information about. That's good fortune. That means that our answer is just going to be 1 over the original slope, or the point at the slope at the original point, which is 1 over 37. If they'd asked us about g prime of 4, well, there's nothing we could do. G prime of negative pi, no idea. But g prime of 6, we can definitely take advantage of because of the connection between x equals 6 and y equals 6 on the original. Another person that needs to make their loud car go. So there is our process. Like literally, there's almost nothing to write here. We're just kind of thinking it through, and we're taking the reciprocal of the slope. So our next example, this is a more advanced question, but I think it's a good one to look at here. Obviously, in a more extended lesson, you'd have more time to think about it and talk about it, but still. It tells us that if f of x is equal to x cubed minus x squared plus 4x, and h of x equals f inverse of x, so we're talking about the inverse of that relation over there, what is the tangent line to h of x, the inverse, at x equals 4? So this is a little bit tricky. So this is tricky. We got to look at first kind of an inventory, and then we'll have a little bit of algebraic work to do. So first of all, a couple things that I can note here is that we're talking about f, and we're talking about its inverse h. And of course, we have interest in the slope of f at a particular point, and we have interest in the slope of the inverse at a particular point as well. So as far as information we know, it asks us what is the tangent line to h of x at x equals 4. That means what we ultimately want to find is h prime of 4. And that means the point of interest for us will be on the inverse when x equals 4. And because of the relationship between inverses, we know that that means that we're interested in when the y value is 4 on the original function. So we need to figure out when the original function is equal to 4 so that we can sort of unravel all of this. We need the x value for the original so we can find its slope, etc., etc. So let's do that. It says that we want to find when f of something is equal to 4. Well, right up there, it says f of x is equal to x cubed minus x squared plus 4x. And we want to figure out when that's equal to 4. So we need to solve this equation. Of course, it couldn't possibly be trivial and easy, but that's okay. We get a little bit of factoring practice in here. It's never a bad time for that. So I'm going to subtract 4 over. From here, you could use the box. I know it's a common strategy. I was taught to factor out in these binomial things, like factor it out into two pieces like this. I think it's factor by grouping is another strategy for it. If we do it, we'll have x squared times x minus 1 plus 4 times quantity x minus 1, and that leaves us with an x minus 1 GCF we can factor out and leave us with x squared plus 4. So in this case, we need to solve this equation. This one's pretty easy to solve. We get either x equals 1 or x equals plus or minus 2i. And I'm just going to go ahead and tell you that we're not interested in points in imaginary complex number land. Like imagination land, that's the realm of South Park. For us, we're interested in real numbers. So the only solution here that we can validly go through is x equals 1. So what did we just find? We just showed that f of 1 is equal to 4. So that means that f of 1 equals 4. It means h of 4 equals 1. And it means that we're interested in f prime of 1 because that will then give us the slope at the corresponding point. So we've actually got a bunch of the ingredients here. We are going to write a tangent line, so this was valuable information. But we do want to go attack that f prime of 1 bit. We need to know what the original slope is so we can take its reciprocal. So I'm going to calculate f prime of 1. Well, first, f prime of x is going to be 3x squared minus 2x plus 4. If we evaluate that at 1, we're going to get 3 minus 2 plus 4. That's 7 minus 2, or 5. So that means the slope on the original function is 5. And according to what we've done, like the work that we've done and the explanations and even the proof here that we did, the slope at the corresponding point is going to be 1 over 5. It's the reciprocal of whatever we get at the original point. And given all of that, we can actually finish this off by writing out our tangent line. Basically, our tangent in this case, I feel like if I write tan and it's in pink, it'll be wrong for me. So I'll write a tangent here. Our tangent, it was to h of x at x equals 4. Our y value is going to be 1. Our slope is going to be that reciprocal slope, 1/5. And then we'll have the quantity x minus, and I think it was x minus 4. So I think I got the colors consistent there. It's probably the one part of the lesson I did well. There is the tangent line equation to this particular inverse relation. So there we go. Again, using the same general structure. The difference was we had a lot more of a skeleton here, and we slowly had to work our way back to figure out what went here so that we could then calculate the derivative here so that we could flip it over here. So a little bit tougher for sure. The final thing I have here is a quick little try it. So obviously if you do want to test this out for yourself and give yourself a shot at looking at this relationship, this is a more classic problem. So I'd ask you to do the equation of the tangent line again too. I mean, feel free to do that. Basically, if you want to do that, go ahead and pause the video now. Otherwise, I'm just going to do the problem really quickly. Did you pause? Cool, let's do it. So it tells us once again at the very beginning as we jump in here that h is equal to f inverse. So we've got another inverse relation. It also tells us that h of 3 is equal to pi. So I'm going to go ahead and start my little inventory here. So we have that h of 3 is equal to pi because it's given. And we also have f prime of pi equal to 2/5. So it's kind of interesting. They gave us some info about h and they gave us some info about f prime. Well, that's more than enough for us to finish out the problem. Here's the way we can do it. First, since h of 3 equals pi, that means f of pi is equal to 3. Helpful for us to have that information. Second, because f and h are inverses, if we want h prime of 3, that's going to be the reciprocal of our slope at the corresponding point, which means it's going to be 1 over 2/5, which we should know is the reciprocal 5/2. Now, since we were trying to find the equation of the tangent line to h of x at x equals 3, we have all the ingredients that we need right here. Our tangent line will be y minus pi is equal to 5/2 x minus 3. And there is the tangent line that we were looking for. Again, not the most exciting problem in the world. Feels pretty repetitive after the work we'd already done. But there is our concept illustrated nicely. Does it match what I got here? Yes, it does. So having said that, basically this was just a really short lesson. It was a little disorganized compared to what I would normally put together. But again, I'm trying to kind of throw this in a few minutes that I had to spare. Hopefully this is enough to get you some good information and answer those questions for yourself since we didn't get to answer them when we originally were prepared to. So thank you for watching. Have a great night.